Assalamualaikum warahmatullahi wabarakatuh and good day to Dr. Ahmad Hussein bin Abdul Hamid. Today I'm going to explain regarding our mini project for MEC 656 Aerodynamics entitled Unmanned Aerial Vehicle Design. Me, Muhammad Asyraf bin FAKHRUL ANUAR, as the first presenter will explain my part on introduction, literature review, problem statement, objectives, and lastly is significance of the project. Since 1951, Malaysia has been affected by the El Nino phenomenon more than 12 times. It created a significant period of haze and drought, which create additional difficulties in Malaysia, including environmental concerns, the economy, and health. Thus, cloud seeding has been implemented and it is now necessary to reduce the effects of El Nino. So, what is cloud seeding? Cloud seeding is a method of forming rain by diffusing seeding agents, such as dry ice and argentum iodide aerosol, into clouds to increase the process of ice molecules. So, the use of unmanned aerial vehicle or UAV, which is a pilotless aircraft, may be an alternative solution for implementing the cloud seeding procedure. So, what is UAV? UAV is an aircraft that can be controlled remotely by humans from a ground station. Next, I'm going to proceed with literature review. So this literature review will cover three subtopics. The first one is range of Reynolds number, followed by drag coefficient, and lastly is airfoil selection. The UAV has helped us focus on low Reynolds number aerodynamics. To solve these challenges in the construction of low Reynolds number airfoil, a straightforward design process was used. For takeoff and landing in the intermediate flow range, the Reynolds number based on the wing's average aerodynamic chord is 1.3 times 10 power of 5 and 2.4 times 10 power of 5. Flow at this low Reynolds number is called transitional since the airfoil has significant camber and a strong pressure gradient along its chord. For the drag coefficient, the wing, empennage, landing gear, and sensor bay drag components were all evaluated in this linear analysis and were underestimated by 10% to account for factors like interference drag and propeller generated flow. So as we can see here, this is the drag coefficient formula. The last subtopic for literature review is airfoil selection. So, proper airfoil selection is one of the most essential elements in the wing design process. Finding a universal airfoil that works in all flying situations and aircraft design is difficult. Thus, XFLR5 is a free program for numerically analyzing airfoils, wings, and whole airframes. This software employs a nonlinear lifting line in its calculations and works with Reynolds number. So now I'm going to proceed with the problem statement of this project. As young engineers, we were assigned to design an unmanned aerial vehicle or UAV to carry out cloud seeding operations in order to cut operational costs and risks, since flying traditional aircraft require human pilot. Thus, the objectives to comply with the problem statement are to study and design airfoil of UAV based on the requirements. Next, to apply theoretical in designing UAV for cloud seeding. And lastly is to analyze the airfoil of the UAV. So this is the significance of the project. The results of the study will help the Malaysian government to evaluate the best UAV design to carry the task of cloud seeding operations to reduce the operating costs as well as to minimize risk. The recommendations of using an UAV as new solution for cloud seeding process to promote rain during drought season, especially by El Nino phenomena, has become necessary to be considered to overcome the current limitations of cloud seeding process in Malaysia.
Thank you to Muhammad Asyraf for his part. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad FAKHRULLAH bin ROZAIRIN. So for my part, I will present regarding the methodology. In obtaining the best wing design, a proper way needs to be applied and followed. This can be seen in the figure, wing design flowchart. Then, our team members have agreed to select 3 airfoil wing sections. These are NACA 6412, NACA 2412, and NACA 5412. However, the comparison between the type of airfoil is important in order to determine the best one for the design. Dr. Hussein had provided us with some information on wing vertical location, which is same with Cessna wing design, although this team also used only 2 wings for our design. The data such Reynolds number are important to complete the analysis of the airfoil in XFR5 software. The software will present data like CL against AOA and plotted the graph after all the parameters have been inserted. All the three types of airfoil will undergo the same procedure. After the process is done, the graph will be transferred to Excel. Moreover, this can help us in completing the mission requirement which to determine the best airfoil to be used. So these are the graphs that we got from the software. This graph included for NACA 6412, 2412 and NACA 5412. We proceed with the aerodynamic design requirement. The table shows the estimation of aerodynamic wing design for the UAV. The requirements such as wingspan, area, chord and aspect ratio are based on the configuration of proposed UAV, ASCE UAV. The proposed UAV, which is ASCE UAV1, is expected to operate at minimum surface ceiling of 2000 meter, which is suitable with our project mission requirement, which is 9000 feet. Also, it proposed for the cloud seeding project. Then, we calculate the estimated for our cruising lift coefficient based on the literature review. From that, we get the value of 0.18. However, we must set the minimum estimated for the cruising lift coefficient due to safety factor, and the value we get is 0.24. So that's all for my part. Proceed with Muhammad FARUQ. Thank you.
Assalamualaikum. My name is Muhammad DANIAL HAKIM bin MUHYIN. I'll be presenting on the aerodynamic design requirement and the airfoil analysis. First of all, few requirements had been applied to our design, such as the angle of attack is 3 degrees, the wingspan is 3.2 meter, 0.44 chord, the aspect ratio is 8, and the last requirement for design is in-wing area, which is 1.5 meter. All of this will contribute to UAV. But before I proceed, I'll explain a little bit about UAV and what it stands for. It is unmanned aerial vehicle, which is powered the vehicle that operates without human operator. Next, the principle it uses aerodynamic force to provide vehicle lift and can carry payload. The estimated cruising lift coefficient used are 0.18, and next, the minimum cruising lift coefficient is 0.24. For this slide, the airfoil analysis being carried out with NACA 5412, NACA 2412 and NACA 6412, and the comparison can be seen in the table. First thing first, they have the same thickness ratio. As example, if there is different thickness ratio, the best one should be the highest. They also have a common which do not sensitive to surface quality. Next, the angle of attack that are close to the cruising lift coefficient is the best, and in this case, NACA 2412 is the closest one. Other than that, NACA 5412 is good between the other choice, as the angle of attack or maximum lift coefficient is the highest. The stall characteristic for NACA 5412 and NACA 2412 are type B, whereas the NACA 6412 is type A. The lowest drag coefficient goes to NACA 5412. The lower the drag coefficient, the better. Next, NACA with the lift coefficient of minimum drag coefficient, which the closest value to cruise NACA 6412. When lift coefficient divided by drag coefficient, the highest value is good, that is for NACA 2412, and for lift coefficient of CL divided by CD, the lowest best is 2412. Moreover, the lowest pitching moment coefficient is NACA 6412, which is the best. However, the three NACA have cruise lift coefficient inside the drag bucket. And lastly, the highest best lift curve slope is NACA 2412. Based on the table, the highest score point is NACA 6412, that means is the suitable to be used in this project. In order to get the intended wings, we had decided then NACA 6412 as our choice.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad FARUQ bin Abdul Aziz. First of all, I would like to say thank you to Muhammad Fakhrullah for the previous presentation. Now, I would like to continue the presentation on the concept generation and also final design. So, first of all, we go to the concept generation. In wing designing process, our team have considered on several manipulated parameters such as lower in parasite drag and also lower in this drag. So with having a tapered wing and swept back design at the leading edge, we highly believe that the wing design can make the UFV at the best performance. Our concept design aims to create a wing with exceptionally lower drag, so resulting in fuel savings for the aircraft during the flight. So from the table below, from the score, ASCE UAV has the highest score among the others. Thus, we have decided to choose the wing design with nearly same concept with ASCE UAV as the wing criteria that was shown by this flight is satisfying. So next, we go to the final design of this project. So basically the wing is divided into two sections, one for the wingspan and another for the height lift mechanism. So the wingspan of the wing is divided into two sections. Wing portion 1 is depicted in this right hand side figure and it is being positioned. So the span, root C, tip C, sweep and the hydronaut parameters were used to adjust the values of the parameter values. So the values of the parameters are shown in this table. As you can see, for the span, we have 1.66 feet, root C 0.4344 feet, tip C we have 0.27 feet, and last one we have sweep for the 9 feet. So next we go to the section 2 of this final design. So section 2 of the wing has been built to handle height lift devices, which aid in increasing the amount for lift for the aircraft. So this table below show the display values for the parameters used in this section 2 to design the height lift device. So the right hand side figure displays the final design of the section 2 wing and its location on the wing. Simultaneously, the table displays the settings that have been selected to accomplish the desired height lift device design using OpenBSP software. So here is the final slide of the final design. So the chosen wing form plays an important part in aircraft design modification, and each style of wing selected serves a distinct purposes. The wing in this study is designed to be swept-back design. The airspeed over the top side of the wings surpass the speed of the sound as the aircraft accelerate, causing a vibration in the planing body. As a result, the sweeping back was purposely oriented towards the back of the aircraft to assure the aircraft stability and vibration at high speeds. The wing chord or wing thickness decreased from the wing root to the wing tip, which is known as taper. The tapering reduced the drag and so enhanced the lift, which is this design works well at the high speed. The extra winglet is a small set of advancing wings that aid in lift generation. Yeah, so in the conclusion, the wing with an inclined angle and the tested angle of attack provide the required lift coefficient when the wing is at zero angle of attack and does not lie off the targeted lift coefficient. So that's all from me. I will pass to Daniel for the next presentation.
Thank you, Muhammad Farooq. Hi, my name is Muhammad Mikhael, and now I will be presenting regarding results and discussion of wing analysis. Now let's take a look at final configuration and specification of wing. Our NACHA 6412 base design wing was evaluated using the PSP Aero program. To begin, the wing has a 0-degree incident angle. The outcome of using the PSP Aero to analyze the lift coefficient at 0 incident angle is also positive. This is nowhere close enough to attain the target value of 0.2408, which is the minimum coefficient cruise. The graph shows that the lift coefficient does not stall because the angle of attack range displayed ranges from -14 to 20 degrees. And the wing's overall specification and configuration are the same as during the idea generation phase. Only the incident angle was raised to 3 degrees. After extensive consideration and analysis, the necessary lowest lift cruise coefficient is eventually achieved. Now, let's take a look at lift coefficient against angle of attack. The CL, lift coefficient, versus alpha examine graph shows a consistent. Then there's the critical 21-degree alpha angle when the plane stalls. The aeroplane may drop its nose until it stabilizes on the correct flight path. Because CL's declination is gradual, the stall is trailing edge. At low angles of attack, the trailing edge of the wing begins to separate from the remainder of the wing. It offers increased agility and control even at high angles of attack. When compared to comparable NACHAs, the maximum CL lift coefficient of 1.693 is considered high lift. The default incident angle is 3 degrees with a lift coefficient of 0.2767. Since the graph is still linear, charting is employed to establish this. Okay, the desired minimal lift coefficient cruise is determined at 0.2408. This figure maintains the plane's height when cruising by offsetting the weight. The CL value is bigger than CLC minimum, hence the cruise lift coefficient is met. Due of the high lift coefficient and alpha value, there is a significant enhancement cause drag. The induced drag coefficient is proportional to the coefficient squared lift. It reduces the aircraft speed and requires more fuel to compensate. A plane with a high lift coefficient has many benefits, but utilizing it for cloud seeding is not recommended in low altitude zones. High speed drag can create severe structural stress. To reduce induced drag, the wing's aspect ratio should be raised. Now, let's take a look at drag coefficient against angle of attack. The drag coefficient is defined as the drag force divided by the dynamic pressure force. The fundamental drag coefficient incorporates skin fraction and shape. This figure shows the drag coefficient curve whose slope decreases from -14 degrees to 0 degrees. The drag coefficient increases with increasing angle of attack up to a maximum of 22 degrees since 0 degree. When the angle of attack are positive, lift and drag are generated simultaneously. As the stalling angle approaches, the drag coefficient increases fast due to the loss of lift. The CD drag coefficient is 0.24. which is the maximum, is located at 20 degrees of angle of attack. Now, let's take a look at lift drag ratio against angle of attack. The lift to drag ratio versus angle of attack is an important result for picking the best outcomes because it represents the aircraft lift versus drag. The intended wing place on the aeroplane was simulated using the OpenBSD program. The graph shows that the maximum lift to drag ratio is 9.5248, which may be obtained at 10. The lift to drag ratio will start to build from -14 and will continue to climb until it hits 9.5248. The wing's ideal attack angle is 10. Okay, the aircraft's extraordinary efficiency is shown by the highest lift to drag ratios. Overall, the aircraft required only minor angle of attack adjustment to achieve steady low drag flight. Now, let's take a look at drag polar. The lift coefficient 0.257 has 0.00871 drag coefficient. This occurs when the lift coefficient is low due to a low angle of attack. This occurs at a negative angle of attack on the coefficient of friction versus angle of attack cost. The drag coefficient was 0.00808 at CL lift coefficient of 0.6981, which is 0 angle of attack. With 1.6767 as high lift and 0.0446 as high drag coefficient, it will continuously decreases until it reaches 20. An angle of attack from -14 to +20 was properly aligned with the wing model. Now, let's take a look at pitching moment versus aerodynamic center. The airfoil has a pitching moment that generates torque. The applied force must be at the airfoil center, not the pressure center. A pitching moment is a moment that occurs on an axis of a moving object. For example, an aeroplane wing must be balanced for the moment. The aerodynamic center is the airfoil chord line where the pitching moment of coefficient does not match the angle of attack. That is not in the angle of attack range. Okay. This figure depicts the relationship between pitching moment coefficient and angle of attack. This graph shows a downward tendency in the direction of airflow. The airflow has a positive and negative value. Okay. The CM value decreases from -14 degrees to 20 degrees as the angle of attack decreases. The air force moment coefficient is positive from -14 degrees to 0 degrees. And as a result, the nose pitch will move upward. Thank you.